In this section, we want to talk about solving linear equalities in one variable. This is an example of a linear equality in one variable. It's linear because the variable occurs only with the power 1, and there's only one variable, x in this case, so it's a linear inequality in one variable. Very similar to a linear equation in one variable. And we're going to find that solving an inequality and solving an equation are very similar, although they do have a little bit of difference. But before we get into that, we need to review the inequality symbols. Here are some inequality symbols. This symbol means is less than. This symbol means is greater than. This symbol means is not equal to. So, an example, 4 is less than 5. Okay? The symbol starts out narrow by the lesser number and widens toward the greater number. Sometimes we're told to think of it as a monster that's trying to gobble up the greater number. Okay? So then is greater than, if we just turn this around, this is read 5 is greater than 4. Okay? And here 5 is not equal to 4. All of those are true statements. If we make a slight change to the symbols by adding this little line underneath each of them, now it kind of looks like a combination between a less than sign and an equals sign. This new symbol means is less than or equal to. So for example, we could say, again, 4 is less than or equal to 5. That's true because 4 is less than 5. It's also true that 5 is less than or equal to 5 because 5 is equal to 5. As long as it's either less than or equal to, then it's a true statement. What would not be true would be to say five is less than 5. That's false. Okay, 5 is not less than itself. Another example of a false statement would be if we said 4 is greater than or equal to 5. This is also false because 4 is actually less than 5. Okay? So we've got less than, greater than, less than or equal to, and greater than or equal to. And is not equal to is also one that we're not going to deal with as much in this section. We're mostly going to focus on the less or the greater ones. Two features that are the same when solving linear inequalities and solving linear equations are, first, if we add something to both sides. So for example, if I have the true statement that 4 is less than 5, and I add something, the same thing, to both sides of the inequality, then I end up with 6 is less than 7, which is again a true statement. So when we come to things like this, with variables involved, adding the same thing to both sides gives me an equivalent inequality, meaning an inequality with the same solution set. Remember, again, that addition and subtraction are really the same sort of thing. So if I were to subtract the same thing from both sides, it would still give me an equivalent statement. Okay, notice that I started with a true statement. I subtracted 2 from both sides. I ended with a true statement. Okay? Anytime we add or subtract the same thing to both sides of the inequality, meaning the expression to the left of the inequality symbol and the expression to the right of the inequality symbol, we're going to get an equivalent inequality, an inequality with the same solution set as what we started with. The second thing that's the same is if we multiply and also divide, because multiplying and dividing are essentially the same. But that is only true if we're multiplying or dividing by a positive number. So, for example, if I have 4 is greater than or equal to 2, that's a true statement. And if I multiply on both sides by a positive number, then I'll get 12 on one side, 6 on the other. It's still true that 12 is greater than or equal to 6. This also works with dividing, like I said. If I were to divide on both sides by 2, say, I'll get 2 is greater than or equal to 1, which is still true. So I can multiply or divide on both sides of an inequality by a positive number, and it will give me an equivalent inequality. We now have all the tools we need to solve the inequality we had at the beginning. 2x minus 3 is greater than 9. We want to solve that for x. Well, let's proceed just as though it were an equation, as though this greater than symbol were actually an equals symbol. What would we do? We're trying to isolate x, so we need to get this constant on the other side. So we add a constant to both sides. Since we're adding, that's not going to affect the inequality symbol. So we have 2x is greater than 12. Now, if this were an equation, we would divide by 2 to get rid of this coefficient. So let's go ahead and do that. And what happens, I get x over here and 6 over here. And again, I'm dividing by a positive number, so the inequality symbol is unaffected. And so my solution is x is greater than 6. Well, this brings us to a few differences between solving an equation and solving an inequality. The first thing is, if I solve an equation and I get x equals 6, it means the same thing if I write 6 equals x. So I can just go ahead and turn them around. I can switch the sides of the equation and it makes no difference. However, if I have something like x is greater than 6 and I switch them around, it is no longer true that these are the same. These are different. Okay? If I want x to be greater than 6, that means I'm talking about everything that's greater than 6. So 6.5, 7, numbers that are larger. This one says 6 is greater than x, which says x has to be less than 6. These are almost opposite statements. So I can't just switch the sides of the inequality unless I also reverse the inequality symbol. If I have x is greater than 6, that does mean the same thing as saying 6 is less than x. So if I were to go through and solve an inequality and I end up with x on the right side, but I'm used to seeing x on the left side, so I want to reverse my sides, I can do that as long as I also reverse the symbol. Okay? So there is the first difference between solving an inequality and solving an equation. The second difference is that my solution is an inequality rather than an equation. If I solved an equation and I came up with x equals 6, my solution set is just the point 6. It's that one value. If I go through my inequality, and I get this for a solution, that represents many values. Like I said, 6.5, 7, 8, 6.2, many, many, many values. Any number that's greater than 6 is a solution to this. Okay? If I were to substitute any of those numbers in, okay, all of these are true statements, which means all of these are solutions for that variable x to solve this inequality. So we no longer just get one value, we get a whole interval of values. There are three common notations in math that are used to express intervals. One of them is set builder notation, and it looks a lot like this. We incorporate the statement x is greater than 6 into our set notation. So we put our set braces to show what's inside is going to be the members of our set. We say our set's going to consist of all the x values such that x is greater than 6. Okay? The second notation is a notation specifically designed for intervals called interval notation, and it basically represents the interval by listing the two endpoints. An interval goes from one point that's least to one point that's greatest. In an interval like this, where x is greater than 6, this is an infinite interval, so the least point is 6. The greatest point, since there actually isn't one, we represent that as positive infinity. So in interval notation, we write our least and our greatest, separated by a comma. Now we also have to surround these with either a parenthesis or a bracket, and that's going to tell us whether or not this number is actually part of the set. Okay? 6 is not part of this set we're describing here because we want x to be greater than 6, not equal to 6. We represent that with a parenthesis. Therefore, we're also going to represent the infinity with a parenthesis, not because we have a parenthesis here, but because infinity is never contained in the set because it's not even a number. So an infinity will always have a parenthesis on it. So that's how we would represent it in interval notation. Graphical notation, we draw a number line. We typically mark 0 as a reference point. I need to label my endpoint, okay? And what I want is everything greater than 6, which on the number line is going to be everything to the right of 6. So just like in interval notation, I'm going to use a parenthesis, and to show that I'm going all the way to infinity, I'm going to shade on the number line everything to the right. Just as a side note, this is only one possible notation. There is another notation used where we would use an open circle instead of a parenthesis. But we are going to use a parenthesis because it matches up with interval notation.